Hi, my name is Zhenhao. Today I will present our paper, Speed Up Training with Variable Length Inputs by Efficient Batching Strategies. Data batching is commonly used for efficient node training, and zero padding is a technique that is used to make samples inside one batch at the same length, in order to facilitate efficient matrix operation and save computational cost. This figure shows 6 batches data with 8 samples in each batch. The shorter samples inside one batch is padded with zeros to make them as long as the longest sample inside that batch. There is some drawback of zero padding since it creates computational overhead. To solve this problem, you can simply sort samples before batching, but it removes all the randomness, which may hurt the model performance. A better solution can be sorting samples in a smart manner that is still maintaining some level of randomness. For example, using the proposed Semisolid batching algorithm and doing some post-processing after batching, such as batch randomization. Also, we can apply some other techniques along with sorting-based data batching strategies, such as using dynamic batch size. In this presentation, we will first cover the proposed semi-sorted batching algorithm with a demo example. Then, we will compare it with two reference sorting-based batching strategies, namely the bucket batching and the alternative sorting batching. By selecting the right parameters in each of these three batching algorithms, we can ensure they have similar randomness level and compare them fairly. Later, we will introduce dynamic batch size along with the semi-sorted batching algorithm. We will also discuss some other data batching operations, such as performing data batching per epoch with different random seeds and doing batch randomizations after batching. In the result session, we will evaluate semi-sorted batching with the combination of other techniques, such as dynamic batch size and batch randomization, with the setup of training TTS models based on NVIDIA Tacotron 2 recipe. Finally, we will give conclusion and future work. These three figures give an example of batching 48 samples into 6 batches, with batch size 8, using random batching, semi-sorted batching, and sorted batching. As you can see, semi-sorted batching is similar to the sorted batching, but with some randomness in the sample length when sorting. The randomness level is measured by zero padding rate or average batch length. To add some randomness in sorting, we perturb the sample length by adding a pseudo-length epsilon I to the actual sample length xi when sorting. The pseudo-length added in is a uniformly distributed random variable, which is bounded by the maximum and minimum length of the samples. The variance of the pseudo-length variable is determined by R, a local randomization factor. There are two reference batching strategies, which are bucket batching and alternate sorting batching. Bucket batching is a two-step approach: sort and then divide. It sorts samples and divides them into different buckets. Then it randomizes samples inside each bucket. The bucket size must be the multiples of batch size to avoid the state jump inside a single batch. The second figure here shows an example of bucket batching. There are 3 buckets, and inside each bucket there are 2 batches. As you can see, the batch length from one bucket to another bucket is sorted, and within one bucket the batch length is randomized. Alternative sorting batching is also a two-step approach: divide and then sort. It divides random samples into bins and ascendingly or descendingly sort samples in the odd or even bins. The bin size should be no smaller than batch size, but it is fine to have one batch across 2 bins, since sample lengths inside that batch are still within a small range due to the alternative sorting. The third figure shows an example of alternative sorting batching. There are 4 bins and 6 batches data. As you can see, the second and fifth batches are crossing 2 bins, but the variance of sample length inside the batch is still small. To compare semi-sorted batching along with bucket batching and alternate sorting batching, we set up the experiments based on Tacotron TTS model training with LG speech dataset. In the training set, there are 655 batches with batch size 16. By selecting different values of the tuning parameter in each of the batching strategies, we can select different randomness level. The first row of figures shows how the randomness level in terms of zero padding rate increase when we increase the value of the parameter. The randomness level for this batching algorithm is always in between the randomness level of random batching and sorted batching. To ensure a fair comparison, we carefully select the value of each parameter so that all these three batching algorithms have similar randomness. After sorting the batch length of these batch methods with selected parameters, you can find the average batch lengths are also similar. After evaluating using this setup, we reached the conclusion that the semi-sorted batching performs similarly to the bucket batching and alternative sorting batching in terms of both training efficiency with respect to the minute per epoch and the model performance with respect to the validation loss. However, the semi-sorted batching has a simpler concept and a smoother tuning parameter, the local randomization factor. It allows easier tuning for the desired randomness level. In the previous example, the batch size is a constant. However, for the batch with shorter batch lengths, it is possible to enlarge the batch size to make the batch area, which is the batch size times batch length, as a new constant. It further speeds up training by fully utilize memory at all times rather than trading off randomness. The zero padding rate and the average batch length are now the weighted averages, so the values remain comparable to the values in the demo using fixed batch size. To be honest, the zero padding rate and the average batch length in the random batching, semi-sorted batching, and sorted batching are all slightly worse, with higher numbers compared to their counterparts without dynamic batch size, due to the extended batch size. However, the training speed is still much faster due to the significantly fewer number of batches after using dynamic batch size. There are two other operations related to batching, which seems trivial, but they cost no time and helpful to increase the randomness and hence the model performance. The first operation is doing data preparation per epoch, which means performing data batching with different random seeds per epoch. The data batches are the same from epoch to epoch without this step, which eliminates the randomness between different epochs. This operation helps even for sorted batching, since data with the same length may be ordered differently after sorting. The second operation is batch randomization, which means randomize batches after data are batched with any sorting-based batching algorithm. Please be aware that this step is not necessary for random batching, since sample randomization already leads to batch randomization. This step significantly increases the randomness for any sorting-based batching algorithms, since batches are no longer sorted or semi-sorted after it. So the conclusion here is these two operations should always be enabled for any sorting-based batching strategies. We evaluated the semi-sorted batching along with other techniques such as dynamic batch size and batch randomization. Here in the first table, we list 4 types of batching evaluation experiments using TDS model training setup. Besides the baseline experiment with random batching, an experiment of the proposed semi-sorted batching with dynamic batch size and batch randomization. We also compared the semi-sorted batching with 2 referenced batching algorithms, bucket batching and alternate sorted batching, and also the sorted batching with enabling batch randomization. We also checked the effect of batch randomization by removing it from multiple batching algorithms. The major takeaway here is by using semi-sorted batching, especially with dynamic batch size and batch randomization, we can dramatically speed up the training while maintaining similar model performance or even improve a little. The model performance is measured by an objective metric, the validation loss at the early, middle, and late stages of training. The average validation loss across these stages is also listed here for reference. The figure below shows detailed validation loss for 4 different batching algorithms. It clearly shows SSB-DBS-BR has some advantage to lower down the validation loss through the training. The upper right table shows how much percentage of training time can be saved if we use more advanced batching algorithms with combination of different techniques compared with the baseline of random batching. Actually, it reduces more than 40% training time if SSB DBS BR is used instead of random batching. The lower right table did 3 types of comparisons based on the late stage validation loss, namely the validation loss 3 in the left table. It shows the reduction rate on the validation loss is reduced as more and more techniques are enabled, which means these techniques such as SSB, BR, and DBS compensate each other in terms of improving model performance. Finally, we conclude that given the same number of training epochs, the proposed SSB strategy combining with DBS and BR significantly speed up training while maintaining similar model performance. Compared with other batching strategies such as bucket batching and alternate sorting batching, SSB performs similarly in terms of both training efficiency and model performance, but with a simpler concept and a smoother tuning on the randomness level. Some trivial operations such as performing data batching per epoch with different randomization and batch randomization take no time but compensates on the randomness loss. Therefore, they should always be used. In the future, instead of using validation loss, we may also consider using some subjective metrics such as mean opinion score to evaluate different batching algorithms. We would also like to test the proposed batching methods on other applications, such as ASR and speaker recognition or verification. The implementation code is built up based on the NVIDIA PyTorch Tacotron 2 recipe and available through this link. Thank you.